Hello, my name is Ewan Judd. I'm the lead author of NeatSkin, a discrete impedance tomography skin sensor. So NeatSkin is an artificial skin sensor. We use it to infer the location of touch. We employ impedance tomography and machine learning for accuracy. So some of the challenges of sensors in soft robotics are: how do you measure the body dynamics of something that has a high number of degrees of freedom, and also measure external stimuli, but without increasing the output dimensionality too much, the output dimensionality of the sensors. Here the idea was to use a network of conductive fluidic channels. Each channel would have conductive fluid in it, where if you change the length or the cross-section area of the channel, then the resistance would change. So if you constrict the cross-section area, then the resistance would increase. So we next fabricated this sensor out of EcoFlex 0030. The channels were then filled with tap water, which is conductive due to the ions in it. A 3D printer was modified so that there was an indenter which replaced the nozzle. The indenter was a cylinder of 5.5 millimeters, had a force sensor on it, so we could automate the process of labeling each position. We used a 3D printer so each of the measurements could be repeated accurately. In order to make predictions, we used a neural network. One layer has been shown to approximate any continuous function to reasonable accuracy with less risk of overtraining. So that's all we used here, with 5 neurons. For the neural network, there were 28 inputs, which are the 28 signals, and 2 outputs, which are the X and Y of the indenter. To further avoid overtraining, we wanted to have a high number of data points compared to the number of weights we have in the neural network. So the rule of thumb is you want about 10 to 100 times the number of data points as you have weights in a neural network. Here we chose 100 different positions and we repeated them 28 times. So each position was pressed 28 times. The data was split into training, validation, and test data. So the test data was just separated from the rest of the data, and then with the rest of the data, validation sets were randomly selected 10 times. And then you had 10 different models trained with each of the 10 sets of training data. The 10 models were tested on the validation set, and the model that had the lowest mean squared error was selected. And then for the best model, the mean squared error was 2.15 millimeters squared. So of the test data, there was 11 positions that were selected randomly. For each position, we selected 6 predictions for that position. So as a way to define whether the prediction is accurate or not accurate, we say it's accurate if the prediction is inside the radius of the probe, which is 2.75 millimeters from the center, and it's incorrect if it's outside that radius. So for all the test positions, you have 11 positions and then 6 data points for each of those. So 54 out of the 66 were correct, which is 82%. And if you do the mean of those 6, and then you compare the mean for all the 11, then 10 out of the 11 were correct, or 91%. So to conclude, this sensor would be low cost and easy to fabricate, and in future work we'll look at developing this so that it can be put on the surface of a 3-dimensional body.